We talked about the most important one already. We talked about histograms. That is probably the one that's going to be the biggest thing that you see on the AP exam. But for the other types of graphs that they could maybe present to you in multiple choice, a lot of it's going to be, what does this graph tell you in terms of like maximum, minimum, center, average, median, all of those things. So I went ahead and I took our class data and I sorted it from least to greatest. And the first one we're going to look at is different types of stem and leaf plots. So a stem and leaf plot essentially is taking away the tens place. So in our case, the lowest value we had for heart rate was 52, and the highest value we had was 88. So whenever I write my stems, I'm going to write them so that I have a stem for every single tens place that I have. So in our case, we have a stem for 5 for 50, 6, 7, and 8. And I did try to make copies with lines for you guys, and then it just didn't copy on the copy machine, so I'm sorry. What we do then is next to the stem, you are going to put the leaf, basically the ones place. So in our case, if I go from least to greatest, for the 50s, we had a 52, we had a 57, we had a 58. And what this is doing is it's showing us the frequency of every single tens place that we have. So when I go to the 60s, we had a 61, a 68, and anytime you have multiples, you will write them each out. So I had 3 68s, so I wrote 8 3 times. And it always has to be in order from least to greatest. And kind of like everything else that we did, it has to have even spacing and it has to be the same size. So if you can get these as uniform as possible, that's going to be what shows you your different things like center and shape and spread, which is what we're going to talk about. For the 70s, we had a 72. We had 73. Let me scroll. We had 75, 77, 78, 78. And then for the 80s, we had 83, 84, 86, 87, 88. And what we do with these types of distributions is we talk about 4 things, technically. We talk about center, shape, spread, and outliers. In this case, most of our data is pretty compact. We have all of them in a very similar range. If I had someone who drank like a monster, like immediately before coming in the room or chugged it, they may have a pulse rate that's a lot higher than everyone else, and we would consider them potentially an outlier. So if I had somebody who had like 110 pulse rate, which is very, very high in comparison to what we have, they may have either just ran here or consumed a lot of caffeine. Now, one thing that you always have when you graph these is a key. And so I usually pick the first value, in this case, 52. And so I'm going to say 52 is a pulse rate of 52 beats per minute. And what you'll find, and I know sometimes it can be a little annoying, we have to be very descriptive in what we do. So I can't just say 5/2 is 52. It has to be specific to what you are talking about. When I went around and looked at everyone's graphs, one of the things I mentioned was, do you have a title? Yes, you can sort your numbers perfectly, but do I know what that data represents? So make sure you actually include the context of this. So I have my regular stem and leaf plot. Now, what else? I also asked you for your gender so that I could show you what a back-to-back stem plot is. So whenever you're doing a back-to-back stem plot, basically one side, the left side, is going to be one type of variable. Most likely it's going to be a categorical variable, so I did gender. The little note I will make here is you want it to be relevant. So you're always going to use the same stems because we have the same set of data. If I were to go in and say, I'm going to sort everyone by if they have dark eyes or if they have light eyes, that may not necessarily have an effect on your pulse. So make sure that the variable you're selecting actually is relevant to the information. If I were to sort people between do they have a pet or do they not, that would have no effect on your pulse. So because of that, it wouldn't be useful. So I'm going to go ahead and I'm going to do the female data first, just because it's the one that looks like what we've been doing so far. So for the females, they started with a 57, 58, and then we have 68, 68, 69, 69, and then 72, 5, 7, 8, and then 83, 84, 88. Okay, that's female data. That side of the graph we treat exactly the same as what we're used to seeing. I'm going to do a key. I'm going to say 5, 7 is a female, because we will have a key for each side, pulse of 57 beats per minute. Now, for the male side, whenever you do a back-to-back stem plot, it is going to be the smaller numbers are going to be closest to the stem. So when I sort my male data, I'm going to start with the 2 being the closest to the stem of 5. And then I'm going to have 61, and then you're going to work your way out to the left-hand side. So I put the 8 to the left. So it's always smaller numbers closest to the stem. And then we're going to have 73, 78, and then we can have 6, 7. Now, what we look at when we have these types of stem and leaf plots, a lot of it is going to be comparison of maximums, minimums, medians. And so what you can do is you can kind of eyeball where you think the center of data would be. A lot of what we'll do will have more data points in it than what we had from our class, but you're able to see on the male side, the smallest value is 52. On the female side, the smallest value is 57. So you're able to make comparisons between the two groups that you collect. So for the male side, we'll do a key is whenever you write the left-hand side of a back-to-back stem plot, you are going to write it exactly the way you see it. So I know that I still wrote the 2/5. However, that is going to be is a male pulse of 52 beats per minute. And what we'll do next class period is we'll talk about how to get these measures of center, spread, and outliers and things like that from graphs like these. Usually, for the most part, if you're able to have a stem and leaf plot, one of the big benefits of it is you get to keep your data. So whenever I do the histograms, we talked about how you're going to lose your data when you start sorting it into bins. If I look at the histograms we made this morning, I can see that there is 2 values between 70 and 74, but I don't know what those values are. I just know that there's 2 of them. So we're able to see like how frequent the numbers are, the intervals are, but we lose the actual data. When I look at a stem and leaf plot, I can see I have 3 values for females in the 80s. And I can see exactly what those 3 values are. It's 83, 84, 88. So one of the benefits for this is you're able to keep the exact values. However, if you had like a really large data set, so say you had like 1,000 people that you sampled for their pulse to see if caffeine had an effect, it would be a really, really big stem and leaf plot, and you probably wouldn't want to do it for 1,000 people. At that point, we're leaning more towards the histogram. But small sets of data, stem and leaf plots are really nice. Okay, the last type of stem and leaf plot is a split stem. So the way this works is, in our case for this particular set of data, we have a smallest number of 62. Let me double check. Yes, 62 and a largest number of 96. So what's going to happen by split stem? Every single stem that we have is going to have 2 rows. So I'm going to write 6 twice. I'm going to write 7 twice, 8 twice, and 9 twice. And the way that we sort this data is row 1 is going to have digits ending in 0 to 4. So in terms of 60, 60, 61, 62, 63, 64. And then row 2 is going to have digits ending in 5 through 9. So that's going to be 65, 66, 67, 68, and 69. The one question I get every single time we do split stems is, can I decide which stems to split? So say, for instance, you have a bunch of 80s and then not so many 60s, 70s, or 90s. If you are doing split stem at all, they all have to be split, even if a stem is empty. So say there's no values between 65 and 69. You cannot skip over it. So whatever you decide, if you are deciding to split that data, and usually you can decide to split that data when it's like 10 or more values in a particular row, everything has to be split. So it's like it's all or nothing. Now, what we're going to do is I'm going to talk about ways you can sort your data really fast using your calculator. So the first thing I want you to do, and I'm going to write some calculator instructions, is I want you to go to Stat. There's a Stat button on your calculator. I want you to go, you're already in the Edit menu as soon as you hit Stat, but we're going to go to One, Edit. And that should take you to the lists. And in your lists, you're going to type this table, type data in L1. So go to your calculator, go to L1. If you need to clear a list, so say for instance someone used it before you and they have different numbers, it may be the numbers that you need, but if they have different numbers, you can go all the way up to L1 and hit clear and enter. Or you can reset the calculator. That's always a good and easy, quick method. Go grab a calculator. Thank you. So type in your data values, and then we'll talk about how your calculator can help you sort it, because sometimes you get really large data sets and they're not in order from least to greatest. So you should have 3, 6, 9, 12, 24 values. Gentlemen, go grab a calculator for me, please. Grab a calculator. All of you are doing it. Yep. Because when I get questions later of, Mrs. Martinez, how do I sort my data? I'm going to say too bad, so sad, because I already taught it. So go to L1, type in your data, and I'm going to write out our instructions for sorting whilst I do that. Type in your data values already so fast? Yes, you have to do all that. We're all doing that. Stat edit, type in your data. Once you have your data in your calculator, you're going to hit the stat button again. And if you go to option number 2, it should say sort A. And I'm sure you can figure out there's a sort A and there's a sort D. A is for ascending and D is for descending. So that would mean greatest to least. For the most part, you want to be least to greatest just because that makes the most sense. So that's why we use sort A. But once you have that, you're going to hit enter. I'm going to open my calculator just so you can kind of see what I'm talking about. Let's flip it over. Is it going to log in? Okay, you should have your data. Once your data is in your calculator, I'm going to switch over so you can see what I'm talking about. You're going to go back to, this is not the data, but you're going to go back to stat. You're going to go to sort A. So you're going to go down to option number 2. And then you can tell it to sort any list that you want. All of my data is in L1. So I'm going to type second number 1 and then hit enter. Your calculator should say done. And when you go back to stat edit, your list should be in order from least to greatest. So when you get to your practice today, because the data in your practice is not sorted, in order to sort it from least to greatest, this is what I would suggest you do. Now, you can always do the old school method of sorting it yourself by hand, but sometimes that takes a really long time. So if I were you, I would familiarize myself with how to sort this data in your calculator, because it could save you a lot of time, especially if you mess up. If you sort it by hand, that usually becomes a problem. You have to erase everything and start all over. I would suggest calculator above anything in terms of data. The only issue with the calculator sometimes is you type in the wrong thing. So double check that your numbers are correct. Eventually we'll get to a point where we're checking if our mean is correct and things like that. And that's an indicator that your data might be typed in correctly. But calculator steps, if you know you're going to forget them, I would say write them down. Now let's go ahead and let's sort this into the stems that we need it to be in. When I go in and I look at these test scores, I can see we got a 62, which is between 0 and 4, and we have a 69, which is between 5 and 9. Jump to the 70s in my list, 74, 75, 78, 79, and then we have 80, 80, 82, 84, 84, and then we have 5 8s. 588s. And then jumping into the 90s, and 96. You will always have a key. So I'm just going to do a 62 is a 62% on an Algebra 2 Advanced Unit 1 test, because that's what it tells us the data is from. Now, the reason why a split stem was good in this case, if I were to just do single stems for the 80s and the 90s, I would have stems that are like 10 numbers long. That's not terrible. It's not the end of the world, but I like to see if I have really long stems from these types of graphs. Sometimes you have a lot more in the upper digits versus the lower digits, and this kind of goes back to deciding on the right bin size. If I were doing this in a histogram fashion and I had a bin of 10, I may not see exactly where the peak is in terms of, is it in the 85s to 89s or is it in the 80s to 84s? But when I split them, make the bins a little bit smaller, I can kind of see that difference. Okay, so these are the 3 types of stem and leaf plots. You have the regular one, you have the back-to-back, you have the split. Know how to read them. You probably will not be making them yourself, but they will ask you questions about a stem and leaf plot and how it relates to describing a distribution. The next one, I'm going to kind of breeze through because you have for sure seen this one. This one is a dot plot. Basically, every single value that we have is going to get represented by a dot on our graph. So I went ahead and took this table, typed it into my calculator, sorted it, and then I'm going to scale my x-axis, so 39, 40, 41, 42, 43. I usually, if I'm deciding bin size or scaling, I'll kind of find the max minus the min and divide it by how many lines I have. And that usually spaces things out pretty nicely. So I have 35 to 50. You always need some type of label on your test for Unit 1. If I ask you to make a graph and there is no label, you will lose points. So you have to have a scale, you have to have a label. So in this case, it's representing Algebra 2 Advanced quiz scores. And then what you're going to do for your dot plot is you are going to make sure that you are drawing your frequencies for how many times these numbers occur in our table. So I, again, went through, sorted my data in the calculator, and I'm just counting how many times I see each number. So for 42s, 3, 4, 5, there's 6 times where a student scored a 42 out of 50. Again, you don't necessarily have to use your calculator. You can kind of do the cross-off method. Every time you use a number, mark it out. But I do think it saves a little bit of time, especially if you get to be pretty quick with typing numbers into your calculator by doing it digitally and not having to sort it yourself. I always like to come in when I do that and double check that I have the right amount. So I'll go count all my dots and make sure it matches what I have on my table. So I have 45, 46, 48, and 50. Now, one thing about these distributions, I've mentioned it kind of briefly. We do talk about multiple things. We talk about center, we talk about shape, we talk about outliers, and we talk about something called spread. And when we see these distributions, the center is kind of what you think it is. Basically, where do you think the center of your data would be? So in our case, our center is most likely going to be somewhere around a score of 42. And usually we represent this by the mean or the median. And then for the shape, what we'll start talking about next time is this, for the most part, my curve is looking real wonky. This, for the most part, appears to be symmetric, meaning the left side closely mirrors the right side. I want you to get it out of your head that it has to be a perfect mirror. As long as it looks like it's curving up and there's a peak, we're good for the most part. This is what we'll eventually refer to as a normal curve, meaning it's unimodal, one peak, and it has symmetry. And then we have outliers. For the most part, there doesn't look to be any true outliers in this data set. If I had someone who scored like a 2, potentially I would consider that student to be an outlier because it would be so far off from where our data is. And then we have spread. Spread is if you have a lot of distance between your minimum and your maximum value. Most likely you refer to it as range. We won't use range a ton. We'll eventually get to things like standard deviation and interquartile range. So in this case, we don't have a ton of spread. A lot of the scores are between 35 and 50, which isn't a big difference between them. So dot plot, basic, dot for every single value. Let's go ahead and let's look at the last type of graph that we have. This is a cumulative relative frequency. And so what that means is, if you think back to what we did last class period, a relative frequency was a count over the total. So we did this for the president's state of birth, and we did it for their political party in the 1.1 notes. And what I need you to kind of highlight and make sure you know, a percentile will tell you what percent of data falls below a value. So what I like to say, percentile is at or below. When you take the ACTs or the SATs, whatever you take, they give you a report, and generally, I think it says something along the lines of you scored in the 95th percentile for math or whatever. What that means is you scored higher than 95% of the people who took that test. So when someone has a baby and they deliver the baby and they start measuring their length and their weight, they look at the size of this baby compared to all the other babies born. So if you're very short, they'll say like you're in the 70th percentile for height, meaning most likely when you grow up, you're going to be relatively short because they kind of follow those trends of how small you are as a baby to how big you end up as an adult. Yes?
70%, is that, so that's like low?
Lower, yeah.
But would it still be above average?
So it's about average, yes. But it's probably like in like the 5.2 to 5.5 range. So it will depend on, so sometimes they'll classify you by weight first and then kind of go into height and things like that. But usually when you're like in the 99th percentile for height, that doesn't necessarily mean you're going to be like 7 feet tall. It just means you're going to be taller. Okay, so anytime you see a percentile, it's always at or below. So when I go in and I say, we have data for the 46 US presidents and when they took office, we have the frequencies. So they went in and they counted how many presidents fell between these intervals, so these bins almost. And so in order to get the relative frequency, I'm going to go in and I'm going to take each value, and because they did a sample of 46, I'm dividing it by 46. So I went in and did the algebra, plugged it into my calculator. You'll notice that I am rounding to a whole number. And that's because when I go in to graph this, I'm going to kind of eyeball where these things are. So when I eyeball it, it doesn't matter that it's 4.2 versus 4%. So rounding to a whole number in these cases is fine. In most of stats, I tell you rounding to a whole number is not great. But if you're doing a cumulative relative frequency graph, it makes the most sense. 26, and then I got 15, 7, 2, and 2. Now, with this rounding, with making it so that everything is a whole number, you will run into the issue of some rounding error occasionally. Generally, it's not huge. So if you get something like 98, 99, 100, 101, 102, that is okay. If you're adding these things up and you're getting like 120%, you rounded incorrectly somewhere. So I divided this in my calculator, multiplied it by 100. That's how I got my percentages. The cumulative part of this is the fact that we're going to take these values and we're going to add them up as we go. So when I look at this first column, all I have is the first column. So it's just 4%. But when I look at the second one, I have the 4% from the first one and this 15% from column 2. So that means I have a total of 19%. And then I kind of work my way up. I have the 19. I'm adding in 28. So that's going to give me 47%. I have 47. I'm adding in 26. That's going to give me 73. And you should start to make your way up to 100%. 88. 88 plus 7. 95. 95 plus 2. 97. And 97 plus 2. 99. And so, again, like I mentioned before, you may potentially end with some rounding error, but you do want to be as close to 100% as possible. You shouldn't get anything like 90 or 110. That would be way, way off. Now, what I'm going to do with this is going to be the values that I actually graph. So the important part from this table is going to be these values that we found in the end. Now, you do need the relative frequencies in order to find these values, but this is the part that's actually going to be graphed. So I'm going to just copy this over because I don't want to have to scroll up and down. 4, 19, 47, 73, 88, 95, 97, 99. Okay, the way this is going to work. These are just values I got from the table before. Didn't do any math. I just copied them over. So don't wonder where they came from. Now, I know you don't have a perfect scale. Eyeball it as best as you can. We're going to have grace because you don't have lines kind of like I do. What we scale the y-axis as every single time, no matter what, if you are doing a cumulative relative frequency graph, you're always going to scale it to 100. I usually say 10 is fine because you don't want it to be too big of a graph. So on your y-axis, scale it by 10s all the way up to 100%. And this is the cumulative relative frequency. And then, just like I do for histograms, whenever I'm scaling the x-axis, I'm going to take all of these lower bound values. So I'm going to start with 40, and then I'm going to have 45, 50, 55, 60, 65, 70, 75. And then I always go one higher just so that my graph is completely labeled. This is age, bless you, US presidents took office. And I try to do my labels as soon as I start scaling things so that I don't forget, just as a piece of advice. Because again, you will lose points on tests. They will not give you credit on the AP exam. You gotta have labels and scales. Now, the way this works is a little weird. So I like to show it to you as a histogram first, and then we kind of talk about what is actually the cumulative part of the graph. So if I was looking at the 40 to 45 range, it looks like it has a frequency, a relative frequency of 4%. So if I were to draw that, I would draw a bar between 40 and 45, and it would have a height of about 4. And then, just moving to the next one, if I go to the 45 to 59, or 45 to 49 range, that had a height, a cumulative relative frequency of 19. So I would draw, if again, speaking as if this were potentially a histogram, I would draw another bar right next to it that had a height of 19. Now, that is not the cumulative relative frequency. That's a histogram of relative frequencies. But the part that's important, you have to think of it visually like it's a bar. And on the top right corner, you are drawing a dot. So when we start, we're kind of starting at 0, and then we're jumping to 4%, we're jumping to 19%, we're jumping to 47%, 73%. And so every single time I go to the next starting value, I'm jumping with the cumulative frequency. So I literally am just drawing a dot where that percentage is. So I have 73, and I know you're eyeballing this, so don't feel like if you have something that looks way off from what I have, if they ever ask you to do this, it would be a very scaled graph that they would have for you to fill in. 88, most likely you would be answering questions about this and you wouldn't actually be graphing it yourself. But what you'll notice is we should get eventually, every single time you see one of these graphs, to 100%, because everything has to total to 100%. And so the way they connect these is they connect them with straight lines. And I know we have the urge to connect them with curves, with like a smooth curve, and it's going to look like a curve for the most part. But every time they connect it with a linear equation, which you will not have to calculate or anything like that, but it's straight lines all the way across. Now, the point of this, again, because you will most likely just be reading it, you won't actually be graphing it. The first question they have is, at approximately what age is the 30th percentile? So the way I find this, and it may not be the same exact value you have on yours, just again, because you're eyeballing it. If I want the 30th percentile, I go to where 30 is on my y-axis, and I draw a straight line across to where my curve is, quote unquote. And so I like to draw the lines just because it hopefully makes it a little bit easier for me to line everything up. And then once you're there, you draw a line straight down. And so this is going to represent the 30th percentile. And so if this were a question on the AP exam, if it was multiple choice, there would be a clear answer. They would have a value like 51 or 52 or 53, and then everything else would be vastly different. They're not going to give you those 3 answer choices and be like, oh, you picked 51. Actually, it was 52. They're not going to do that to you. It would be like 52 and 62 and 72 and 12. And so you pick the one that is the clear answer. If it were an FRQ, they would give you a range where they would accept value. So they may take anything between 51 and 54 and say that works for us. So it's not going to be something where you're like, oh, my line is slightly different than yours. I got 54 and you got 52. They're not going to be that nitpicky about it. So the way we answer this, at approximately what age is the 30th percentile? We'll say age 52 represents the 30th percentile. And we'll say meaning. And if you encounter a problem where there is a follow-up question, you have to answer the follow-up question. AP exam, when they start breaking down those grading rubrics, if you only answered 52, they're not giving you credit. You have to answer everything. So meaning less than 30%, because a percentile is at or below, of US presidents. And you always have to have context. Were inaugurated before the age of 52. When I told you guys on the first day of class that this was going to be more writing than you probably have done in any math class, I mean it. You will have situations where you have to include context, and writing the number answer just is not going to suffice, especially in terms of FRQs. That is where most people get a majority of their points. From what I've seen the last 9 years, more people do better on FRQs than they do on multiple choice, because multiple choice is a lot of reading and it's a lot of weirdly worded questions. Okay, in the reverse sense, if I wanted to find a percentile giving an age, they told me that Nixon was 56 years old when he was inaugurated. I do the same thing, but in reverse. I go to where 56 most likely is. I draw a line all the way up to where I think my graph is, and then I draw a line over to the percentile, and it looks to be roughly like the 51st percentile. And so, same thing, I'm going to go in, I'm going to say he is at about the 51st percentile. So let me write that out. Nixon is at approximately the 51st percentile. And then I'm going to answer their follow-up question. What does it mean? Meaning he was older than 51% of US presidents at inauguration.